Right. So very good morning to you all. I welcome you all for today's EM session. In my last class, I have discussed about the Biot-Savart's law and magnetic field due to a current in a straight wire. I am doing the derivation of magnetic field due to a current in a straight wire. Right. So Biot-Savart's law. What is meant by Biot-Savart's law? Biot-Savart's law states that the magnetic field due to a current carrying wire, the magnetic field due to a current carrying wire or filamentary conductor, it is also called as filamentary conductor, is directly proportional to current element and sine of angle between current carrying conductor and a line joining point P and differential length, and is inversely proportional to square of distance, right? Distance between point P and current carrying conductor. That is, DH is proportional to ideal sine alpha by r square, and the proportionality constant is 1 by 4 pi. So therefore, DH is equal to ideal sine alpha by 4 pi r square. So from cross product definition of cross product, we can write DH bar, right? So DH bar is equal to ideal cross AR bar by 4 pi r square, right? So like this we can write, and the direction of magnetic field can be determined from the right hand thumb rule, right? Maxwell right hand thumb rule. If you hold the current carrying wire with your right hand, with the thumb pointing towards the current, then the other fingers curling in the direction of magnetic field. So thumb indicates the direction of the current, and the remaining fingers indicates the direction of magnetic field. If current direction changes, the direction of magnetic field also changes. So similarly for electrostatics, where it is possible to have continuous charge distributions like line charge, surface charge, and volume charge. Here also in magnetostatics, it is also possible to have line current, surface current, and volume current. Ideal is line current, amperes. KDS is surface current, ampere per meter. JDV is volume current, ampere per meter square. And a related problem, small problem we have done, right? And we are discussing the magnetic field due to a current in a straight wire, right? So this is similar to field due to field due to line charge in our previous chapter, which we have discussed in our previous chapter. So this is similar to field due to line charge. So magnetic field due to a current in a straight wire. So if you look at the figure, the current carrying conductor is considered on z-axis, which is indicated in red color, right? Extends from A to B. So this is the current carrying conductor, right? Finite in length, right? Which extends from A to B. And my interest is to determine magnetic field at a point P on y-axis, right? So point P is 0, y 0. It may be anywhere on y-axis you can consider, or else you can also consider on x-axis, or else you can consider on yz plane also, or xy plane, anywhere, whatever the point maybe you can determine magnetic field. For convenience, I have chosen point P on y-axis. So procedure is very simple. the same procedure which we have followed earlier, joining the lower end, right? Green color line joining the lower end, and that makes an angle alpha 1, joining the upper end, that makes an angle alpha 2 with the z-axis. And let us consider a differential element, right? So this is a small length, right? So determining magnetic field over the entire length is difficult, but whereas determining magnetic field with respect to small length is very easy. So that's why here we are considering a small differential length dl, right? So we will determine magnetic field at point P with respect to this differential element. So that integrating we will get the magnetic field due to the entire length. So this differential element is considered at 0 z dash on z-axis, and that makes an angle alpha, right? That makes an angle alpha, and the length between point P and differential element is r, right? Is r, and rho is the normal distance. Rho is the normal distance between what? Between point P and the axis on which the current carrying conductor is considered, right? So that is the normal distance rho, right? So from Biot-Savart's law, right? So that is equation 1 is Biot-Savart's law, right? So in equation 1, dl is dz dash az bar, because current carrying conductor is considered on z-axis. So therefore, and the element, differential element is considered 0 z dash. So therefore, dz dash az bar, and r bar is the vector distance, right? Vector distance between and the 2 points, right? So what are those 2 points? Right? Vector distance between um, 0 z dash and 0 y0, right? So this is point P, and this is the differential length, right? So we are determining magnetic field at 0 y0, right? At this point, we are determining magnetic field at this point, right? So therefore, this point minus remaining, that means 0 minus 0, y minus 0, 0 minus z dash, like that. So y minus 0 ay bar and 0 minus z dash az bar. So we will get y ay bar minus z dash az bar. So r bar is equal to rho aero bar, and this is in cylindrical coordinates. And r is the scalar distance. R bar is the vector distance, and r is the scalar distance, right? And ar bar is r bar by mod r bar. Those things we have determined in our last class, right? And as shown, substitute dl r ar bar in equation 1, we will get, right? So let us do it, right? So dh bar is equal to dl. So what is dl? dz dash az bar ideal, right? Ideal cross ar bar, right? Ideal cross ar bar is rho aero bar minus z dash az bar divided by root over rho square plus z dash square, and 4 pi r square, 4 pi r R is rho square plus z dash square whole square, right? So this is R square, right? So let me make it clear to you. So this is dz dash az bar is dl, and this term, so this term is ar bar, and this term is r square, right? So I hope it is clear to you. Now simplifying, right? Simplifying this, so what we'll get, I so let me give you the simplified equation after simplification. I rho dz dash a pi bar divided by 4 pi rho square plus z dash square power 3 by 2, right? After simplifying, you will get this one, right? So because az bar dot arrow bar is a pi bar, and az bar cross not dot cross az bar is equal to 0, right? So here in this equation you can see az bar cross arrow bar and az bar cross az bar, right? So az bar cross arrow bar is a pi bar, right? So this you will get, right? And this is dh bar, right? So magnetic field due to differential element. And now h bar. So what is h bar? H bar is the magnetic field due to the entire length extending from A to B as shown in figure. So therefore integrating I rho dz dash a pi bar divided by 4 pi rho square plus z dash square power 3 by 2 alpha 1 to alpha 2, right? So these are the limits, alpha 1 and alpha 2. You can see in this figure alpha 1 and alpha 2 are the angles, right? So therefore the limits are in terms of alpha 1 and alpha 2. So therefore we need to integrate with respect to alpha, right? We need to integrate with respect to alpha, but here dz dash, right? Dz dash. So dz dash means we are integrating with respect to z dash, right? With respect to z dash. So therefore let us convert, right, the given function in terms of alpha, right, in terms of alpha. So to do so, from figure, right, from figure, let us assume, right, let us assume, so this is O, right, O P, let us say this point is C, right? So this point is C and this point is P, right? So let us consider COP, triangle COP, right? Let us consider triangle COP, right? So therefore triangle COP, right? So let me draw triangle COP, rectangle triangle COP here, right? So this is point C, O origin and C, and this one is z dash, and this one is alpha, and this is rho, right? Same COP. So in this figure, COP is a rectangle triangle. The same rectangle triangle I have reproduced here, right? So in this figure, right? So CO is z dash and OP is rho, right? So from this, right, from figure, tan alpha. So what is tan alpha? Opposite side by adjacent side, right? Opposite side by adjacent side. Therefore, z dash is equal to rho by tan alpha, or rho cot alpha, right? Z dash is rho cot alpha, right? So therefore, dz dash, right? Dz dash is equal to minus rho cosecant square alpha d alpha, right? Differentiating this. So differentiating this, dz dash is equal to minus rho cosecant square alpha d alpha. With respect to alpha, we are differentiating this. So differentiation of cot alpha is cosecant square alpha minus cosecant square alpha, right? So therefore, dz dash is equal to minus rho cosecant square alpha d alpha, right? So let us say this is equation 3, right? So therefore, substituting equation 3 in equation 2, right? Equation 3 in equation 2, what we'll get, h bar is equal to integral alpha 1 to alpha 2 I rho minus here dz dash, right? So dz dash is minus rho cosecant square alpha minus rho square cosecant square alpha a pi bar divided by 4 pi rho square plus z dash. So what is z dash? Rho cot alpha, right? Rho square cot square alpha whole to the power of 3 by 2, right? So this you will get, right? So that means by substituting z dash, so this is z dash and this is dz dash, right? So substituting these two, right? Substituting these two in equation 2, right? Substituting these two in equation 2, we will get this one, right? So in the denominator, you can take rho square common, right? Inside the brackets, you can take rho square common. So if you take rho square common, you will have 1 plus cot square alpha, right? 1 plus cot square alpha is cosecant square alpha, right? And simplifying, right? And simplifying, you will get this one minus I by 4 pi rho, so that can be taken outside, alpha 1 to alpha 2 sine alpha d alpha. This you will get after simplifying the above equation, you will get this one, right? So minus I by 4 pi rho integral alpha 1 to alpha and a pi bar, right? Simplify, you just simplify the above equation, you will get on this one, right? So this you will get. So integrating, sine integral is minus cos, right? Sine integral is minus cos, and substitute the limits alpha 2 and alpha 1, and finally you will get this one I by 4 pi rho cos alpha 2 minus cos alpha 1 a pi bar. So this is the final expression for magnetic field due to a straight wire, right? Magnetic field due to a straight wire carrying a current I, right? So very important, right? So this is the magnetic field due to straight wire, right? Magnetic field due to a straight wire, right? So in this expression, we need to know clearly the different parameters, right? So what are those? Rho, right? So rho is one parameter, right? And you need to know that very clearly. Rho is one parameter, and alpha 1 is another parameter, alpha 2 is another parameter, and a pi bar is another parameter, right? So these are the four parameters, right? So when a problem is given, we have to determine all these four parameters, right, to complete a problem. So rho, so what is rho? Rho is a normal distance, right? Normal distance from point P to the axis on which straight wire straight wire is considered, right? Rho is the normal distance from point P to the axis on which straight wire is considered, right? So in this figure, you can see. So this I have explained in the last class itself, right? So this is rho, right? So this is rho. So rho is the normal distance from point P, right? From point P to the axis, right? So in this figure, it is PO, right? So O is the origin. So in this figure, the normal distance is PO. In this figure, not all the case it is PO. It may differ based on given problem, right? So here in this figure, the normal distance is PO, right? And similarly, alpha 1. So what is alpha 1? Alpha 1 is the angle between, right? Angle between what? So here you can see alpha 1. Alpha 1 is the angle between z axis, in this case z axis, because the current carrying conductor is considered on z axis. If the current carrying conductor is considered on x axis, it is with respect to x axis. If the current carrying conductor is considered on y axis, it is with respect to y axis. So therefore the angle between the axis on which current carrying conductor is considered and line joining lower end to point P, right? Line joining lower end to point P. So that is the angle, right? So angle between the axis on which current carrying conductor is considered and a line joining lower end and point P. Is it clear? So alpha 1 is the angle between axis, right? So z axis and a line joining lower end. Lower end means A. A is the lower end to point P is the angle alpha 1, right? And coming to alpha 2, right? Coming to alpha 2. So what is alpha 2? Alpha 2 is the angle between the axis on which current carrying conductor is considered and a line joining upper end and point P, right? Almost same. The above statement is almost same. So therefore, I will combine, right? I will combine those to alpha 1, uh, alpha 1 and alpha 2. So here upper end, right? Upper end, right? So lower end is for alpha 1, upper end is for alpha 2. So alpha 1 is the angle between axis on which current carrying conductor is considered and a line joining lower end and point. And whereas alpha 2 is the angle between the axis on which current carrying conductor is considered and a line joining upper end and point P, right? Upper end and point P, right? So that is alpha and alpha 2. And one more thing is very important observation. Alpha 1, right? Alpha 1, for example, if you consider the triangle BAP, right? If you consider the triangle BAP, right? So BAP is the triangle. For this triangle, alpha 1 is the outer angle, not inside the triangle. Alpha 1 is not inside the triangle ABP, right? So alpha 1 is not inside the triangle, it is the outside, the angle outside the triangle. Whereas alpha 1 is the inside angle, right? Alpha 2 is inside angle, alpha 1 is outside angle. So that is very important observation, right? So alpha 1, so alpha 1 is outside angle and alpha 2 is inside angle, right? Alpha 1 is outside angle and alpha 2 is inside angle, right? And now a pi bar, right? A pi bar. So what is a pi bar? A pi bar is equal to, what is a pi bar? Here you can see. So a pi bar is az bar cross arrow bar is a pi bar, right? So a pi bar is equal to az bar cross arrow bar, right? Az bar cross arrow bar. What is az bar? What is az bar here? So this is az bar, right? Along the increasing component of z. This is az bar, right? Along the increasing current. What is the direction of current? This is the direction of current, right? So therefore, az bar is nothing but direction of current, right? Az bar is nothing but direction of current. Direction of current, right? So in the figure, the current is flowing in positive z direction, right? And arrow bar. So what is arrow bar? Arrow. What is rho? Rho is the normal distance, right? So therefore, arrow bar is the unit vector along the increasing component of rho, right? So this is arrow bar, right? So this is arrow bar. So that means rho is along in this case it is y-axis, ay bar, right? In this case it is ay bar, right? So not all the time it is AY bar, it may differ, right? So in this particular case, aero bar is AY bar, right? Aero bar is AY bar. So therefore, aero bar is the unit vector along the increasing component of rho, right? Aero bar is a unit vector along the increasing component of rho. So rho is the normal distance, right? So you have to remember these points very clearly, right? So rho is, as we know, rho is the normal distance from point P. Rho is the normal distance from point P to the axis on which straight wire is considered. Now alpha 1 and alpha 2 are the angles, and alpha 1 is outside angle, alpha 2 is inside angle. That you please remember. And A pi bar is AZ bar cross aero bar, where AZ bar is the direction of the current and aero bar is unit vector along the increasing component of rho, right? So these are the important points to be remembered, right? And one more important point is this is the magnetic field due to a straight wire of finite in length, finite in length, right? The length of the straight wire which we have considered on z-axis is finite in length, right? So now if the length of the conductor is infinite, right? If the length of the straight wire, right, straight wire is infinite, right, is infinite, then alpha 1, alpha 1. So what is alpha 1 here, right? Infinite in the sense what? Infinite in the sense when a is at 0 0 minus infinite and b is at 0 0 infinite, right? When point a is minus infinite and point b is infinite. So therefore the straight wire, long straight wire is infinite in length, right? So if a, right, if a is infinite, what is alpha 1? If a is infinite, what is alpha 1? Hmm? If a is infinite, what is alpha 1? Alpha 1 is 180 degrees, right? 180 degrees. If b is at infinite, alpha 2 is 0, right? Alpha 2 is 0, right? So if you want more clarity, let me explain like this. So y-axis and z-axis, right? And this is the current carrying conductor which we have considered on z-axis, A, B, right? So this is the point of interest. This is alpha 1 and this is alpha, right? So for example, if point A is here, right? If point A is here, then what is alpha 1? If point A is here, so what is alpha 1? joining, and this one is alpha 1, right? This one is alpha 1. Let us say alpha 1 dash, right? If point A is at here, alpha 1 dash. If you compare alpha 1 dash and alpha 1 dash is greater than alpha 1, right? Alpha 1 dash is greater than alpha 1. Alpha 1 is less than 90, alpha 1 dash is greater than 90, right? That you can tell very easily, right? So if you extend A to infinite like this, if you extend A to infinite, then alpha 1 dash or alpha 1 will become pi degrees, right? Go on increasing, right? Greater than 90, go on increasing, and it will become 180 degrees, right? If A extends to minus infinity, it will become 180 degrees. So similarly, alpha 2, right? So this is alpha 2, and let us say so this is z axis, and let us say let me consider point B here, right? Let us consider point B here, and if you join point B to point P, it will be like this, and this is alpha, this is alpha 2, and let us say this is alpha 2 dash, right? So if you compare alpha 2 dash and alpha 2, alpha 2 dash is less than alpha 2, right? Alpha 2 dash is less than alpha 2. So therefore, go on increasing B towards positive infinite, right? If you go on increase point B towards positive infinite, then alpha 2 will become narrow and narrow. Go on increasing B, point B, it will become narrower and narrower. So therefore, alpha 2 will be 0, right? At infinite, alpha 2 is 0. And at minus infinite, alpha 1 is pi degrees, right? So therefore, alpha 1 is pi, and alpha 2 is equal to 0, right? If the length of the straight wire is infinite in distance, right? So therefore, h bar is equal to I by 4 pi rho cos alpha 2 minus cos alpha 1 a pi bar, right? So this is the equation. I by 4 pi rho cos alpha 2 minus cos alpha 1 a pi bar, right? And alpha 1 is pi degrees and alpha 2 is 0 degrees. Substitute. So if you substitute this, you will get I by 2 pi rho a pi bar, right? I by 2 pi rho a pi bar, right? So this is the magnetic field due to an infinite straight wire. Magnetic field due to an infinite straight wire, right? So this is similar to electric field. E bar is equal to rho L by 2 pi epsilon naught rho a rho bar, right? So rho L by 2 pi epsilon naught rho a rho bar, right? So this is the electric field due to infinite straight wire, right? Electric field due to infinite straight wire. So similarly, this is the magnetic field due to an infinite long wire or straight wire, right? So that is the comparison between electric field and magnetic field, right? So with this, we have completed magnetic field due to a long straight wire, right? And now let us switch on to or let us do a related problem here, right? So let us do a small problem, and then we will close the session. Right? So problem 1. So problems are very important. The conducting triangular loop in figure below carries a current of 10 amperes. Find magnetic field at 0, 0, 5 due to side 1 of the loop, right? So figure is like this. Zero, center is 1, and this is 2. So this is a loop, right? So loop in the sense closed, carries a current I, right? So this loop carries a current I, and this one is side 1, and this is side 2, and this is side 2, right? So this is the problem, right? So solution. So the conducting triangular loop in figure below carries a current of 10 amperes, right? So given data, I is equal to 10 amperes, and find magnetic field at a point P 0, 0, 5, right? So with respect to side 1, right? So point P 0, 0, 5 in the sense what? 0, 0, 5 in the sense z-axis. On z-axis we have to determine. So here this is x-axis and this is y-axis. So therefore z-axis is this, right? So this is z-axis, right? So therefore on z-axis we have to determine, right? On z-axis we have to determine, right? So formula h bar is equal to 4, sorry, I by 4 pi rho cos alpha 2 minus cos alpha 1 a pi bar, right? H bar is equal to I by 4 pi rho cos alpha 2 minus cos alpha 1 a pi bar. So this is the magnetic field, right? Magnetic field due to a finite length of conducting wire, straight wire, right? So in the problem it may be infinite or it may be finite. We will consider this h bar is equal to I by 4 pi rho cos alpha 2 minus cos alpha 1 a pi bar, and let us say this is equation 1, right? So I is given, and we have to calculate rho alpha 1 alpha 2 and a pi bar, right? So we have to calculate all these parameters, right? So to determine all these parameters, Let me redraw the figure. This is Z, X, and Y, right? So with respect to side one, right? With respect to side one. So therefore, side one, right? Side one is this. So the length of the side one is 2, right? 2 units, right? So therefore, this is 0, 1, 2, right? So this is side one, right? So at a point, at this point, so this point is 0, 0, 5, right? On z-axis 0, 0, 5. So we have to determine magnetic field. So what is the procedure? Joining the lower end, right? Let us say lower end, lower end in the sense and the end which is nearer to point P, that is lower end, right? The end which is nearer to point P, right? So let us say this is A and this is B, right? So A is lower end, right? So join lower end, so joining lower end. So this is lower end to point P, which is nothing but z-axis, right? Straight away z-axis, on z-axis. So this is the line joining lower end and point P. And similarly, upper end and point P, upper end and point P, joining upper end is B, right? Joining point P, right? And what is the normal distance? What is rho here? So rho is the normal distance from point P to the axis on which straight wire is considered. On which axis straight wire is considered? On x-axis straight wire is considered. So therefore, the distance from point P to the axis on which, what is the axis on which we have considered? X-axis, right? So x-axis we have considered. So therefore, rho. So rho is straight away 5, right? Rho is straight away 5 because the lower end is at the origin and point P is on z-axis. So therefore, the distance from origin to point P is 5. So therefore, rho is 5, right? Now, alpha 1. You indicate alpha 1 and alpha 2 here. So what is alpha 1? As per the definition which I have given. So here you can see alpha 1. So what is alpha 1? Alpha 1 is the outside angle, alpha 2 is the inside angle, right? And it is the angle between the axis on which current carrying conductor is concerned and a line joining lower end and point P, right? So therefore, from figure, what is alpha 1? Alpha 1 is the angle between the axis. On which axis? The current carrying conductor is considered x-axis. So therefore, it is the angle between x-axis and line joining lower end and point P. So what is the line joining lower end and point P? Which is nothing but rho. Therefore, the outer angle, right? The outer angle, the angle between this one, right? So this is alpha 1, right? Is it clear? Okay, is it clear to you? So alpha 1 is the angle between x-axis and line joining lower end and point P. And alpha 1 is the outside angle, not inside angle, outside angle. Next, alpha 2. So what is alpha 2? Alpha 2 is the angle between x-axis, x-axis means on x-axis we have considered current carrying straight wire. That's why x-axis. So x-axis and line joining upper end is B to point P is this, and alpha 2 is the inside angle, inside, right? So this is the inside angle, alpha 2 is inside angle, right? So therefore, from figure, we can say that alpha 1 is 90 degrees, right? Alpha 1 is 90 degrees and alpha 2. So what is alpha 2? Alpha 2, let us take tan alpha 2, right? So because we know this length. So what is this length? This side is 2 and what is this side? This side is 5, right? So these two sides we know, right? So therefore, tan alpha 2 is opposite side. So what is the opposite side? 5 and adjacent side 2. So therefore, alpha 2 is equal to tan inverse 5 by 2, right? Alpha 2 is tan inverse 5 by 2, right? Clear, right? So this one, right? And alpha 2 and alpha 1 we know, right? We have calculated here. Let me write. So alpha 1 is 90 degrees and alpha 2 is, you calculate how much it will be, tan inverse 5 by 2, right? So that, and a pi bar. So what is a pi bar? A pi bar is equal to az bar cross arrow bar, right? So what is az bar? Az bar is direction of the current, right? And arrow bar is unit vector along the increasing component of flow, right? So from figure, let me indicate, right? Let me indicate this. So what is arrow bar? So this is rho. So rho is increasing in this direction. So this is arrow bar, right? So therefore, arrow bar is equal to az bar, right? Arrow bar is equal to az bar and az bar direction of current. So what is the direction of current? So this is the direction of current, right? I, right? I is the direction of current and which is along x-axis. So therefore, az bar is equal to ax bar, right? So therefore, here, right? So here, a pi bar is equal to ax bar cross az bar, right? Ax bar cross az bar, which is equal to minus ay bar, right? Which is equal to minus ay bar, right? So therefore, all the values are known. Rho is equal to 5, alpha is equal to 90 degrees, alpha t is equal to tan inverse 5 by 2, and a pi bar is minus ay bar, right? And substitute all the values, simplify, you will get the answer, right? So h bar is equal to I is 10 by 2 pi rho. Rho is 5. Cos alpha 2. Cos alpha 2 is tan inverse 5 by 2 minus cos alpha 1 is 90 degrees and a pi bar is minus ay bar. So simplify this and you will get minus 59.1 ay bar milli ampere per meter, right? Milliampere per meter. So this is how we can do the problem, right? So very important, right? So in the next class I will do few more problems so that it will be more clear to you, right?